Now, let's make an example, okay? Let's walk through this as an example. Let's just say that the cognitive process I am interested in is articulatory processes for word repetition. Okay, let's just say that I care about what does it take to repeat a word. Now, I will start by defining a task of interest. So maybe my task will be something like, and here I printed what might be instructions to a participant. Look at the screen, and when you see a word, repeat it. Okay, so here I'm just asking my participant to stare at the screen, and anytime a word appears, they just have to repeat it. This way, I can trigger articulatory processes to repeat a stimulus that is read, okay, which is what I care about. So I'm going to call this the repeat task, right, just for short. And we might do this experiment, and when we look at what parts of the brain are active during the repeat task, who knows that we find these particular regions. And I should say the regions depicted in this little cartoon example are totally random. Well, almost totally random, but they're not meaningful. Okay, so don't interpret where they are exactly. But now let me ask you this. How many cognitive processes does it take to repeat a sentence that you're reading off a screen? In other words, what I'm asking you is, let's say that you have somebody do your task of interest, and now you see these two activations, one here and one here. Are you allowed to say, oh, look, this piece of the brain and this piece of the brain must be very important for repeating? Is that where repeating is in the brain? And the answer is no, because it takes a lot of cognitive processes in order to repeat something that you're reading that are not about repetition. Let me explain. Let's say that I show on screen a word and you read it to then repeat it. How many processes does it take to do that? Well, a number. For one, you probably must use low-level visual processes. I mean, I'm showing you words, but words are lines that combine. So your brain will engage visual processes related to detecting the presence of lines. It will also engage higher level visual processes, for example, combining lines into letters, and then even higher processes where letters get combined into words. And once you combine things into words, that will trigger semantic processes, associating a certain meaning with a certain word, and so on and so forth, all the way up to triggering the motor programs that are needed for repeating that word, for articulating that word, which is the process I care about. So if I only do one task and then look at the activations underlying that task, it doesn't help me much. Or rather, it tells me that my process of interest, the motor programs for articulation, is somewhere in here, but I don't know if it's both or if it's only one or only some small part of one. So I need a way to get rid of all these processes I don't care about and tell which parts of the brain are specifically for my process of interest. Now, in order to do that, we use the subtraction method. Specifically, we'll come up with what I'll refer to as a baseline task or a control task, which ideally includes in it all the same processes as those that are needed to repeat, except for repeating. So I need to create a task that has low-level visual processes, that has high-level visual processes, that has semantic processes, et cetera, except it does not have repetition. So maybe we could create something like this. We could say, now look at the screen, and when you see a word, read it, but don't repeat it. So in other words, we've ideally created a task that might have in it a similar amount of low-level visual processes, since you're reading similar things, a similar amount of high-level visual processes, since again, you're reading words, a similar amount of semantic processes, since you're reading words and that will get associated with meanings, et cetera, but it will lack triggering motor programs for articulation. I'm going to refer to this as the read task. Okay? And maybe we do that and we look at the brain activations during that moment, that period. And who knows, maybe we find out that only these parts of the brain right here are active. So if all has gone well, I can now subtract this task, these activations, from these activations. Right? And I should ideally get rid of all the parts of the brain that were involved in this process, which I don't care about, in this process, which I don't care about, in this process, and all the processes except for my process of interest. And so if I subtract the two, lo and behold, I will find a pattern of activation that should be exclusive, should only be about the one cognitive process I care about, motor programs for articulation. Okay, so my task of interest has a lot of processes, including the one I care. I subtract from it a baseline task that has all the same processes except for the one I care. If I subtract them, ideally, I'm left with the parts of the brain that are important for the specific process I care and no other ancillary process. Now, this is the general way in which we conceive fMRI experiments. However, this approach can go wrong in a number of ways. First, it is conceivable that articulatory processes could be automatic. Once you read a sentence, it's maybe, just too strong to resist. Maybe your brain triggers automatically articulatory processes. Or maybe people subvocally, even without realizing it, they still sort of rehearse the word and repeat it subvocally. So it is possible that the baseline task or the read task, the task that is supposed to have all the processes except for repetition, might nonetheless trigger some amount of repetition, or might nonetheless trigger those motor programs to repeat a word. If that is true, then the activation here would look a lot like the activation here, and when you subtract them, you're left with nothing. And now you would obviously underestimate what parts of the brain are important for repeating. You would say, oh, there's nothing in the brain that is used for repeating, which obviously would be incorrect to conclude. Now, a different issue, although related, what if, just reading something without having to do anything might be boring. Participants might not really care about it. So who knows that, your participant gets bored and just stops reading. After all, they don't have to do anything. So maybe they stop reading. You as the experimenter can't know if they're reading or not. Right? When they're repeating, you can hear them repeat. But when they're reading, if they're not giving any answer, they might not read. If that were the case, let's just assume that you had a participant who said, oh, great, I don't have to do anything. Well, I just have to read. Well, the experimenter can't know if I don't read and do anything, so I'll just mind wander. Close my eyes and mind wander. So what would happen? Well, we would see no activations during the periods of reading, since the participant isn't doing anything related to the stimuli. And so if we subtract this from this, now we're left with both the parts of the brain, both these parts of the brain, and we risk overestimating how many and which parts of the brain are important for articulatory processes. And rather, we would conclude that these are both important for articulatory processes, when in fact we know that's not true. Okay? It's just a byproduct of having a poor baseline, a poor comparison task. Finally, there's a third very important issue, which I was hinting to last time, which is the so-called pure insertion hypothesis. And see, the question about this is this: When you read for the sake of reading, are those the exact same cognitive processes needed to read for the sake of repeating? Right, so are all the processes up to reading the same if you add repeating on top of it? See, this is known as the pure insertion hypothesis. And the idea is that anytime you do a subtraction comparison, you're assuming that there's no interaction between the cognitive components of a task. In other words, if you add an extra cognitive component to some task, so the extra cognitive component being repeating, and if you add that to some other cognitive set of cognitive tasks, such as all those that are needed to read, the assumption is that that does not change, adding this extra component does not change the components that are needed for reading alone. In other words, we assume that reading to repeat and reading to read are the exact same thing. Adding a repetition on top of reading doesn't change the way in which you read. That's the assumption. And see, in behavioral experiments, you can compare that, because if you make a task harder and harder and harder and harder, you can see if the response time becomes longer and longer and longer and longer in some kind of linear fashion. If it's not linear, then it probably means that there's some interaction at play. If instead the relationship is linear, then probably pure insertion is upheld. In fMRI, it's not quite as obvious to test this hypothesis. Let me give you a different example just to explain the idea of pure insertion. Completely different domain, but similar thought. And you have to participate in this, by the way. So pronounce the word, the phoneme P, right? And feel the way in which you're putting your mouth, how you're articulating it. So P. Now my question to you is, if you say P just to say P, or if you say P to say a word that has some other phoneme after that, do you pronounce the P in the same way? Let's make this example. Again, be aware of how you place your lips and tongue and mouth when you say P. And now try saying the word pool. And try to feel if the way in which you say the P in pool is the same as the way in which you say P when you're trying to say pool. And you might feel that the way in which you articulate the P when you're saying, when you attach ool to it, is very different than the way in which you articulate a P by itself. Now you might be able to say pat. And pat, so if you add AT to the P, you will articulate it in yet a different way. So in this case, pure insertion would not hold, because the way in which we pronounce the P changes according to what we do after it. This is just an example to explain what this hypothesis is about. So just the same way in which adding ool to the P changes the way in which we say P, maybe adding repeating something on top of reading might change the way in which we read. This is a crucial hypothesis, because every time we do an fMRI experiment and a subtraction, we are assuming that we can add an extra process on top of something, and that won't change anything else. And it's key, because when we're doing this subtraction, we are assuming that whatever is in the reading here is exactly the same that whatever is in the reading here. And pure insertion is necessary for the subtraction method to work. Because if the reading here is different than the reading here, then when I subtract them, I'm not left just with the one extra process. repeating. I'm left with repeating and all the differences between reading to read and reading to repeat. So the pure insertion hypothesis is at the heart of every single fMRI experiment that is about cognitive tasks. So it's really a crucial hypothesis. Unfortunately, it's very hard to assess whether it holds or not.